Okay, so excuse me. Today I'll be talking about machine learning and Deephaven.learn, which is Deephaven's machine learning um, module, or a submodule of Deephaven, which facilitates the data transfer to and from Python objects and Deephaven tables. So first off, we'll go into some basics. I apologize if this is redundant for any of you who know a thing or two, but machine learning is basically computer algorithms that improve themselves automatically by training on data. Whether that data is labeled or unlabeled will determine the type of machine learning model that is being used. They fall into 4 different categories. There is supervised learning, unsupervised learning, semi-supervised learning, and reinforcement learning. Where semi-supervised learning is kind of a combination of the first two. In the case of supervised learning, you have a training set of data in which you know the answer or the correct labels, perhaps if it's a classification problem, say for example the iris data set. In that data set, we know exactly which iris flower each set of measurements corresponds to. So if you train a machine learning model to classify iris data, you have a labeled set of training data. And I'll actually do that using 2 different algorithms when I do some examples. Unsupervised learning is where there is no there are no labels for the training data. There are a few different approaches. The primary ones that I've used are clustering, which 2 of which I have listed there we'll use today, which is k-means clustering and dbScan clustering, and I'll talk a little bit more about those once we get to the examples. Semi-supervised learning combines the 2, where your training data has a small amount of labeled training data among mostly unlabeled training data. So that's a particularly difficult problem to solve that I'm hoping actually to write up a document or a blog post of some kind where we use Deephaven to do that. And the last one that I have never actually used is reinforcement learning. Basically, it will test out how different actions affect an objective function based on a particular state that a system is in. Say, for example, a pathfinding algorithm, a reinforcement learning system, will test out all of the different paths that an object can take to get to a goal. And so reinforcement learning really is in the same way that maybe someone who already, if you're teaching a child a math subject and they've already learned about it, reinforcement learning will reinforce the things that they know so that they can better apply those to problems that they don't yet know how to solve. So this next slide, I came across this when I was doing some social media scanning. I thought this was pretty funny. What is deep learning? Deep learning is an algorithm that can spot the differences between these cute little doodle dogs and fried chicken. I get a deep learning algorithm may not actually be able to do that. But anyway, deep learning is a very, very hot field right now. Deep learning models are generally neural networks with a large amount of hidden layers. In order to, and the goal of increasing the number of hidden layers is to reduce the effect of diminishing returns as problems become increasingly complex. So while I'm here, here's a picture of a neural network for anyone who's unfamiliar, but you have an input layer, an output layer, and everything in between is a hidden layer. And so a neural network is meant to essentially reproduce the activity of the human brain, which is a bunch of neurons connected by, I think they're called synapses, that send electrical signals to and from. And so I'll talk a little bit more about neural networks when I get into an example. But deep learning is a very hot topic right now. I don't know a whole lot about the approaches to deep learning because I have read some papers where they will have hundreds and hundreds of hidden layers, and I don't know what goes into, defining and creating those models. I just put this slide together right beforehand. There are some really cool applications. I meant to make this list a lot longer. I will put this presentation will be available on the the Learning Drive after this is done. So if anyone knows any really cool applications, please paste them in here. I think the coolest one that I've seen is this. It is something called AlphaStar. Google's DeepMind team built an AI that will play a video game, a real-time strategy video game called StarCraft 2. And it's really cool to watch it play. Even if you don't play the game, this thing just crushed the pros. It was way too good. But it's a really cool application of deep learning and what it can actually do. And StarCraft is a very difficult and complex game, so pretty impressive by then. So I'll be using Python today for machine learning. And I want to talk really quickly about why Python is popular for machine learning. It's got there are four things that I think make Python really good for data science in general, and those are simplicity, accessibility, design, and the Python ecosystem. Generally speaking, data scientists like myself are not as strong of just straight up software developers as your traditional computer scientist. So there's a smaller amount of overhead required when writing Python code, and Python was built with a small core set of functionalities, but it was also designed so that it was easy to create plug and play modules to do all sorts of stuff, and we'll explore a few of those today in these examples. I will use SciKit Learn and PyTorch for the examples today. So here's a list of a few modules. I have some base plus images ready to go for a few of these. Everyone in this list actually, except for XGBoost. And so, like I said, I'll use PyTorch and SciKit Learn today. I particularly like TensorFlow though. Really, it's just kind of a personal preference thing. But I found that TensorFlow and PyTorch are both very powerful for creating neural networks and doing deep learning in general. Whereas Scikit Learn, I much prefer for the data pre-processing tools that it makes available, as well as the classification and clustering algorithms that fall within the unsupervised learning field. I do want to check out a few other of these. I have not used XGBoost. I tried using Theano and wondered why it was giving me a bunch of warnings, and it turns out it is no longer supported. And so anyway, it's this one in particular I'm really excited to try is Natural Language Toolkit. So, as I have done not a whole lot of natural language processing. Okay, so before we get into our examples, what is Deephaven.learn? As I mentioned earlier, it is a tool to convert data between Deephaven table data and Python objects. So with that said, it doesn't actually have to be used for machine learning models specifically. The first example I'm going to do is extremely simple, and we'll just add two columns together using Deephaven.learn. However, the end goal really is to do something more meaningful than add two columns together. So the reason it's called Learn is because it's very useful for applying machine learning models to data in Deephaven.tables. And it's also really useful for applying algorithms to subsets of data in a table. One of the arguments that you supply to Deephaven.learn is a batch size, which you can kind of set to be whatever works best for your approach. And so the alternative prior to Deephaven.learn was basically to convert data to and from Pandas data frames and tables, and that's pretty slow. Pandas data frames are pretty slow in general. Deephaven tables are fast. And so what we'll do today is use Deephaven.learn to automate the conversion of data to and from tables and NumPy arrays and Torch tensors. All of which are much faster than Pandas data frames. So last but not least, the syntax that Deephaven.learn uses is you need 5 different arguments supplied to Deephaven.learn. Excuse me. Your first is a source table with the data you want to process. The second is a model, a function that either trains or applies a trained machine learning model to your data. The third is a set of inputs. The fourth is one or more outputs from your machine learning model. And the last, but not least, is your batch size. And it's worth noting here that if you were going to be training a model on the data and you don't want to actually return anything, learn does not need to be, this result table is optional. You do not need to have a return table from a call to deephaven.learn. Okay, and I'll do 4 examples today. The first one sums 2 columns together, so it doesn't really apply a machine learning model, but it shows, excuse me, how to use deephaven.learn. The second, I will classify the iris data set with a k-means clusterer. The third, I will classify the iris data set using a neural network. And the fourth, I will go through my credit card fraud classification blog example. And that requires some data exploration, so I'll do a little bit of plotting with Deephaven too, and kind of show how that's done. All right, so please disregard the ridiculous amount of scripts I have here. It's like I have a lot. It's kind of like browser tabs, so I can never get rid of them. So anyway, as far as the first example, this is basically only to show how using Deephaven, how you can use deephaven.learn in your queries. It's really easy to do. And so now it's kind of silly to use Deephaven Learn in order to do something as simple as adding 2 columns together, but this is just, again, an example on how to use it. So the first thing we're going to do is create an empty table with 2 columns of data. These columns have some square roots and the negative square root of the square root. I will create a function here with one input. It will basically sum every value in the 2 columns, and then it will return them. There are 2 additional functions we need when we use Deephaven Learn. The first will convert table data to the Python object that you need. In my case, it is a NumPy array. And the second will convert your Python object data to table data. So before I run this, I will briefly discuss these 2 functions, the table to NumPy and NumPy to table. These are also called gather and scatter functions. I believe Alex coined those terms and used those in a presentation he gave during one of his demos during one of the community core meetings. But basically what we'll do is we'll initialize an empty NumPy array of the size we need. Now this IDX is what's called an index set. It is basically the number of rows you have in the table, and then this calls argument is a column source object, which there are 2 columns in our table, so len calls here will be 2, and each object within here it's a magic container that holds all the table data. And then we're dealing with float data, so we'll tell it that. And basically this will just go through and fill up a NumPy array with the data from the table and return it. And then last, this second function, we will be returning data from a Python object back into a table. What we have as output is a column of, a NumPy column of data. And we're going to be feeding the column of data itself, as well as the index of the current value, and all we're going to do is return that value. So it's really simple. And if I run this, we'll see the result table pop up. And so here's our source table. It's got all this stuff. It's got a bunch of numbers, and the result table, once again, has the 2 numbers added together. So it's really simple. And again, you could do this with something else entirely that's probably easier and faster, but this was just the whole purpose of this is just to demonstrate that using deephaven.learn is pretty easy. And so again, I mentioned there's 5 arguments that you want to supply to the call to the learn function. The first is our source table, which we made earlier. Again, I made my function that applies my machine learning model, which just adds 2 columns. It's called summation model. And then we have our third and fourth inputs are probably what we want to talk about the most. So your collection of inputs is going to be formatted as an input object, which is something within the Learn library itself. And so we have two columns that we want to add together. So what we have here is our two columns are encapsulated in these square brackets, which tells Python this is a list. And then we give it a function that will convert these two columns into our NumPy array here. And then the outputs, once again, we have this learn.output. This will convert it from the NumPy array back into our table. And we only have one column here. So in this case, we don't actually need these square brackets, although I do believe it works with the square brackets. No, it does not. Okay.
It actually doesn't.
I think it did. Sorry, go ahead.
Yeah, in an earlier version it did, but really
Okay.
there's here you're mapping a value to a specific column.
Yes.
And so mapping it to multiple columns didn't make sense, so that was taken out.
Okay. And I think I actually have, I know there was a comment from you, Jake, in one of my documents at one point about I think I left square brackets in there once and took it out for another. And I think I fixed that, but I'll just have to go back and check. So again, and then another thing is that's was a little different for me to get used to is that these two arguments are expected to be in the form of a list. So you want to encapsulate this entire third argument in square brackets, and same thing with the fourth argument, even if it's only one column. And then lastly, I set my batch size to 100 here because this table has 100 rows. There may be instances where you don't want to train a machine learning model on all of the data at once. And if that's the case, you can set the batch size accordingly. Okay, so on to a second example.
Let me say one thing on the batch size. So, the batch size is basically how many rows are being crammed into your tensors at a time. And so you may have limitations like the amount of RAM on the machine you're running on, or you may have limitations of the amount of RAM that's on a GPU, and you can control, how much stuff you're processing at once by changing the batch size.
I played around with the batch size when I was doing my credit card fraud example with a neural network and found significantly improved performance from how long it took when I decreased the batch size, so it wasn't doing it on 150,000 data points at once. But it's application specific, and yeah, like Chip mentioned, depending on your memory and some other things as well. Okay, so that's first example. That one was pretty simple. So this second example, what we're going to do is use a k-means or a k-neighbors classifier to classify data in the iris data set. So for anybody not familiar with the iris data set contains 150 observations of 3 types of iris subspecies. The iris flower is measured there are 2 characteristics, there's petal and sepal length and width that are measured. So that's 4 observations that correspond to a classification, which is one of the 3 subspecies. So the first thing we're going to do here is we'll import our data, and then we'll quantize the iris subspecies. So instead of a string, it'll be a 0, a 1, or a 2. Which is kind of necessary for most machine learning applications. You want it to classify numbers as opposed to strings. It's significantly easier. So a k-neighbors classifier, basically it will partition a set of observations into k clusters, where every observation corresponds to a particular cluster that has a centroid. So in layman's terms, a k-means cluster will basically ask if it is querying a particular data point, it will check out what that data point's neighbors says about it, and then classify it into one of the clusters based on its neighbors. So again, we're going to follow the same kind of pattern as last time. We're going to import our data. We're going to construct our machine learning model, which last time was just adding 2 columns. This time, we're going to create a k-neighbors model and train it. And then, it's not really training it since k-neighbors is an unsupervised algorithm. So we'll fit it to our data. we'll use the fitted model, and then we'll check out the results. So in this case, I'm using SciKit Learn to implement the K-neighbors classifier. SciKit Learn I really, really like. It's very intuitive and simple, at least in my opinion, to implement a lot of these models. K-neighbors is not particularly overly complex for a classifier, so it's really easy to implement, and we'll see with a dbScan that I'll use later, which is a much more complex model to implement, that the SciKit Learn, the API itself makes it pretty easy to actually create and apply the model towards data. So this first function here, I'm going to fit the model to our data. So I have, now this data is actually labeled. Our X train is the set of observations, where our Y train is the set of excuse me, of quantized iris flowers. So one interesting thing is that I don't actually want to return anything from this. Since we're actually just fitting the model, I'm going to call learn twice. And the first time I call it, I'm not going to return anything. So there's no return statement here, but I want to have this model as a global quantity so that I can access it from other functions as well. So I'm going to declare it as global here, and then I'll fit it, and then I won't return anything. This second function, I will use that global model that has now been fitted, and I will use it to predict the iris subspecies based on the features, or what is the same thing as this X train variable in here. And then I'll return those predictions. One interesting thing that I've come across is that a lot of times when using NumPy arrays, it will, depending on how many data points you try to classify at once, it will actually squeeze, and that's because of, where did I put that? Sorry, that's down here. It's because of this call to squeeze, that it will remove it'll remove dimensions of size 1 from an array. And so if you operate on one data point, it will return a single value, where if it's more than one, it'll return an array. So this whole thing, which is really the most useful during the dbScan problem, and I'll talk about that in a bit, it will basically ensure that we are always applying our model to an array with the same number of dimensions. So anyway, this will predict the iris subspecies based on the observations. And then once again, we have the same two functions, our gather and our scatter function. In this case, this is going to gather data from a table to a NumPy array. And then this will return the prediction at a particular element in that NumPy array into the table. Okay, and then the first time we call learn, we're going to fit our k nearest neighbors classifier. So in this case, we have no return table. Our source table is the iris table that we read into memory earlier. We have the fit knn function, which takes two inputs. We have an X train and a Y train. So in this case, with two inputs, remember we encapsulate everything in a list. Our first argument is this whole thing here. And so our training features are the four observations that, or the four measurements of the flower itself, which are the sepal length, the sepal width, the petal length, and the petal width. And we will gather those, observations from the iris table into a NumPy array using the table to array function. Our second input is the iris subspecies itself, which is in the class column, and we'll use the same gather function, table to array, to gather that one column into a column, NumPy column vector. We have no outputs here, so we just specify none, and then this batch size, I just want to do this on the entire table at once. There are 150 observations in the table, so I'm just going to specify 150. The second call to learn will actually use our fitted model and predict the iris subspecies from that. And similar to before, our use knn function expects one input this time, which in this case, each Each feature within the features is going to contain 4 observations. So again, we specify all 4 observations. We gather them to a NumPy array using table-to-array. And in the same way as before, we actually have outputs this time. So we're going to call that the classified class, and we're going to spit those answers back out into the table using this getPredicted class, which all it does is return the classified, or basically the prediction at a given index within our NumPy array, and cast it to an integer. And again, we're going to do it on the entire table at once. And so this is in my SciKit Learn document. I removed the printouts that will tell you how accurate this is, but a k-means classifier is about 96% accurate with this data set. It's not nearly as useful as for some other data sets, but you can see here that there is one that's incorrect. This is a 1, whereas it predicted that it's a 2, but pretty much everything else is right on point. I think it gets 3 observations out of the 150 wrong. And again, with SciKit Learn, all it took for me to create, fit, and apply this k-nearest neighbors model was basically this line here. You give it 1 input. I specified 3 neighbors to the k-nearest neighbors, and so it will consider a data point, a cluster, if it has 3 neighbors within some sort of distance. Okay, so now we're going to solve the same problem, but this time we're going to use PyTorch to create, train, and apply a neural network to, excuse me, to the same data set, and we want to classify observations within the iris data set using said neural network. Given the fact that the iris data set is a fairly simple problem, I'm not going to try to create some complex deep neural network. A fairly simple neural network should suffice for this problem. And so once again, we'll read the data into memory. We'll quantize the iris class. And so what we'll do here is we'll construct a neural network with 2 hidden layers. And so this class contains the implementation of our neural network. And so our first hidden layer has 16 neurons in it. Our second layer has 12 neurons in it, and our final output layer has 3 neurons in it. So I kind of picked these values arbitrarily. I played around with a few. I tried, I think, like 10 and 15, 10 and 8, and all of them worked pretty well. I think this one gave me the best results by some small margin. But one thing that's worth noting is that, so what I want as an answer out of my neural network is the class, which is just a single integer. But what I also want is the probability that this model thinks that a particular set of observations belongs to a particular iris subspecies. So given that we have 3 iris subspecies in total, I am going to set the number of output features as 3, because I want each output neuron in my artificial neural network to contain a value between 0 and 1 that corresponds to the probability that this set of observations belonged to this particular iris subspecies. Excuse me. Another thing worth noting is that I am using the rectified linear unit activation function for each for every neuron in this thing. A rectified linear unit, I can actually look it up here. Basically, it looks like a linear, just a straight line. But this activation function is very commonly used. It's the blue line there. It is for values below 0. The applying ReLU will just give 0, and outside of that, it is just a straight line corresponding to basically y equals x. So what we're going to do is create the neural network. We're going to define 2 functions here. I'm going to define our first, once again, that trains our model, and the second that will apply our model. So we're going to use cross-entropy loss as our loss function. We're then going to optimize our neural network with the atom optimizer and a learning rate of 0.01. You can play around with these values and see how it affects the accuracy of your neural network and how fast it will converge to a solution. We'll train it for 100 epochs, and we'll store the loss at every epoch in this loss array. So basically what we're going to do for each of the 100 training epochs is that we will call this forward function, which we defined earlier. And again, the forward function, all it's going to do is apply it's going to apply it's basically going to propagate the Irish observations through our neural network, and then it will back propagate through, calculate the loss using our cross entropy loss here that we set, and then it will put it in there. And after every 10 training epochs, we will print out the loss. And what we should see, and what we will see, is that the loss decreases with each with each set of 10 training epochs, and we'll actually see that it will converge towards a solution a little bit slower as you go through every training epoch. And it's also worth noting that every time we go through a training epoch, we want to make sure to zero out all of our gradients and step forward, which is something in PyTorch that I found is I don't know if you have to do this or not, but in TensorFlow, it's implicit that this is done. However, I've explicitly stated or told the neural network itself to do this when I use PyTorch. Our second function is not going to train the network. We hope that after this first function is called, that our network will already be trained. So all we're going to do is take our trained model and apply it to the set of data. So once again, just like here before, I'm going to check to make sure and ensure that our input data is of the right dimensions. And then we're going to go through every item in our features. So at every step in this loop, it will take one of these rows with the 4 observations. It will apply our model onto it, and then it will append the prediction, the maximum of the 3 outputs. So what we say is that the the output neuron with the highest value is what we consider to be the correct prediction. And it turns out it's right most of the time. So once again, we're going to define the same functions here to gather value from a table to a torch tensor this time. That's the biggest difference really between PyTorch and TensorFlow, is that TensorFlow expects NumPy arrays as your data structure that your training and testing data will be in the form of, whereas PyTorch uses torch tensors. And the only real difference that I've found between the gather and scatter functions when it comes to using NumPy versus PyTorch is that if you saw previously, when we create our empty NumPy array, so we have np.empty here and we have torch.empty here. And the only real difference is that NumPy arrays, when you use NumPy empty here, it expects 2 arguments. The first is a list with your number of rows and number of columns, and the second is your data type, whereas with a torch array, it expects 3 arguments. So basically all you do is get rid of the square brackets around these 2. Kind of a detail that I actually didn't realize a couple times when I was on autopilot and putting these examples together. So anyway, not much is different other than that, there is nothing different between these 2 functions, the gather and scatter functions. So once again, the first time we call learn, we're going to train our model using the function we specified earlier. Our training function expects 2 inputs, xtrain, which again corresponds to our 4 observations, and the ytrain, which corresponds to the iris class. So we're going to encapsulate this whole thing in square brackets so that it's a list. Our first argument will be our 4 observations, and our second argument will be our the class column. And once again, when we train the model, we have no outputs, and we're going to do it on the entire table at once. And in the same way as before, the second time we call this, we will use the the trained model. And it only expects 1 input, which is the set of observations. And then the second time around, we have a return table, and our new column will be called predicted class. And so we run this, and it takes a few seconds, and we'll see how our loss gets smaller and smaller and smaller. And towards the end here, we don't get really much better at all. This is actually one of the big things that deep learning aims to alleviate is these diminishing returns after you get through quite a few training epochs. You'll see that your model will get better. Even at epoch 90, we got better at epoch 80, but by such a small margin that it was probably just unnecessary at that point to even keep training. So once again, we found this neural network works pretty well. It looks like so far I don't see any incorrect. Okay, there's one. We have one incorrect prediction here, but overall this particular neural network, which only has 2 hidden layers, worked really well. And so I guess a simple model is perfectly sufficient for a simple problem. But however, I would be willing to bet that this neural network would perform very, very poorly for much more complex problems. All right, so my last example is a little more in depth, and so I'll talk a little bit more about some data exploration. Oh, I forgot about this script. So this will replay some fake iris measurements for 15 seconds using dynamic table writer, and it will apply our trained PyTorch model to it. So I'll run this, and for 15 seconds we'll see so this is writing iris measurements, or fake ones, and then we're going to make predictions using our trained model. And so this is how a lot of my Deephaven Learn documentation goes. It follows a formula of solve the problem without Deephaven, solve it with Deephaven, and then create some measurements or some live measurements, and we'll apply our model. And so I think it's pretty cool to watch my model work in real time, even though these measurements aren't live and I can't see an application where someone's going to measure flowers once a second and send them to a database. So the last example I have is classifying credit card purchases as fraudulent or valid using something called DBScan. DBScan stands for density-based spectral clustering of applications with noise, and it's a fancy way of saying the ability of an algorithm that can identify clusters that are nonlinear in shape and size from a set of input points. And so, for instance, k-means clustering has its limitations, one of which is it does not work particularly well for clusters that are nonlinear in shape and size. And so we don't want to make assumptions about our input credit card fraud data, excuse me, about the shape or the size of the clusters that we expect to see. So so k-means is likely not a good approach to the problem, and we want something a little more robust, which DBScan is actually very robust to noise. One of the things it's good at is picking out noise from data. And so moving forward, we'll do that. So a little bit more about the input data. This data set is one of the most popular on Kaggle. It has millions of views and tens of thousands. Last I looked, I think it was tens of thousands of code submissions for people who have all sorts of different approaches on how to solve it. When I first wrote a neural network to solve this problem, I found that it just didn't really work at all. And I actually found that there are some people that have written their PhD theses on how to construct a neural network to deal with data like this. And so I didn't want to go into a full PhD thesis for a blog post. So I decided to go with something I've used before, which is DBScan. And I'll talk about that a little bit more in a minute. But as far as the data, it corresponds to 48 hours of credit card purchases made by European cardholders. In those 48 hours of purchases, there are 284,807 purchases in total, of which only 492 are fraudulent. This is less than 0.2% of the total number of purchases. So what we're dealing with here is heavily skewed data, where a fraudulent purchase is so rare that it can be considered as noise amongst the valid counterparts. And we're going to make an important assumption that turns out to work pretty well, although it has its limitations and it is not perfect. And that assumption is that those fraudulent purchases, are so sparse that we will consider them to be spatial outliers, not just regular outliers, but spatial outliers from their valid counterparts. And so if we're going to put this theory to the test, what we want to do is a little bit of data exploration first. So every credit card purchase in this data set has 28 purchase metrics, all of which have been PCA transformed and anonymized because obviously we're dealing with credit card purchases. We don't want any information in there that can identify any of the cardholders in this particular data set. Excuse me. So everything's anonymous. And what we want to do before we try out dbScan is we want to actually see whether or not the idea that data points are spatial outliers or fraudulent purchases are spatial outliers will work. And what we want to do is we want to make a histogram of purchase metrics between valid and fraudulent points. And so what this, I think I need to import my data. Sorry. I thought I had it in here, but I guess I don't. Just need to import it. Oh. So I need to import my data into a Deephaven table so that I can plot it. And so I'm going to read the data into a table called credit card. Now, I can tell you right now that these three columns, V4, so that the 28 anonymized purchase metrics are labeled V1 through V28, and that V4, V12, and V14 are the three columns where fraudulent and valid purchases differ the most. And so the objective of this particular script here is to visualize that using Deephaven's built-in plotting. So what I'm going to do here is just go through the three different columns that I just talked about and plot, make a histogram. Oh, did I run out of memory? No. Oh, I'm running one. Click the wrong button. Okay, so this is going to create a histogram plot, and I want to make this bigger. But basically what we have here is, so this is for column V4, and so this is how the valid and fraudulent purchases are distributed amongst the others. So we see here that the valid purchases are in blue and the fraudulent are in green. We can toggle them on and off. So this is what the distribution of excuse me, our valid purchases looks like for this particular purchase metric. This is what our fraudulent purchases look like, and we can see that there is some overlap, but there is a pretty significant spike here in valid purchases where there aren't too many. For instance, dbScan in this case will probably do a really good job at picking out data in this particular region as outliers. Over here, we want to identify fraud. I had it backwards there. And so there's a lot of fraud out in, from maybe 2.5 upwards to whatever 12.5 here that does not overlap with the valid purchases. So we expect dbScan to do a pretty good job at picking those out and labeling them. However, the overlap is where dbScan will fail, and that's in the case where these green and blue overlaps. And we'll do the same thing for V12 and V14. And we'll see once again that in this case, the valid purchases are constrained to this kind of small distribution here, whereas the fraudulent ones actually cover a large amount of space that valid purchases don't. So I think V12 will do a very good job. V12 will help us quite a bit with dbScan. And then V14, we'll just check that out really quick. Excuse me. So once again, we see that these particular distributions are pretty different from one another. If you were to plot some other ones, basically any of the purchase metrics in the 20s, you're going to see these two distributions look very, very similar. dbScan will do a very poor job in that case because the fraudulent data points look way too much like the valid ones. So that's the first part of our data exploration. So given the fact that we've seen that these three particular purchase metrics have distributions that are relatively different from one another, we are going to exclude all of the other anonymized purchase metrics from our analysis. So that was what I did at the beginning here. I guess I forgot to add the part where I import the data into Deephaven at the top here. But I'm going to exclude all of the other V columns from the table itself. So another, where is it? I want to make sure I'm in the right. Okay, so when it comes to dbScan, actually I have it here. So dbScan, what it will do is that it will query, it's kind of in a similar way to k-means clustering. It will query each point in a data set. It will determine if there are a particular number of neighbors within a particular distance of that data point, and then it will determine whether or not it's a part of a cluster or if it's an outlier from that information. And so what we need to try to do is figure out how we're going to set our two inputs to dbScan so that our algorithm will work well, or that our model will work well for this data. So those two input parameters are the number of neighbors and the neighborhood distance. And so they can be visualized from this picture. The neighborhood distance is the distance from each data point to the circle around it, so that circle radius. And then the number of neighbors in this case probably is something like 3. So we can see that this point A is considered a part of a cluster because it has 1, 2, and 3 data points excuse me, within its neighbor distance. Same thing with this one. It's got 1, 2, 3, and 4. This guy out here has nothing near it, so it's completely noise. Whereas points B and C have at least one point within this neighborhood, but they're considered outliers because there aren't enough. So what we need to do is figure out how we want to set these two parameters. So first we're going to start with the number of neighbors. And so there isn't really a guideline for how to actually pick these values. This value, the general rule of thumb is that you want the number of neighbors to be greater than the total number of dimensions in the data you're working with. Since I have picked out only 3 of these purchase metrics, we are dealing with 3-dimensional data. I want to use a number greater than 3. I'm going to use 10. I tried a few different ones here and found that 10 works pretty well. Now the second input parameter is one that actually there is a pretty standard way to pick the value, and that is the neighborhood distance. And so the way that you do it is you want to find the nearest neighbor distance of every point in your data, and then you will plot them in ascending order, and you will pick what is called the elbow of the data, or basically the point at which the slope of the curve is increasing at the highest rate, so the maximum of the second derivative. And so we'll run this here, and this will create another plot. And what this is doing is it's going to use a KD tree to query every point in the data. It'll get the distance to the nearest neighbor and then plot them in ascending order. And we will hover over the point at the elbow of the curve that we want to use. So here is a plot of the nearest neighbor distance for the last, or basically the largest values from points 30,000 onwards. A little bit about this, I exclude, so I'm considering our training data to be between hours 12 and 16, at least I guess 12 and 16. We're only going to do training on 4 hours of data, and then we will test our dbScan model on the 4 hours that are 24 hours after our training set. And we're doing that because of the assumption that we expect purchases to look, basically, we expect purchases to be similar enough between one day after the other within the same time window. And it turns out that actually works pretty well. So anyway, I plot here the nearest neighbor distances in ascending order for points 30,000 onwards. So it's 30,000 to 31,200 or something. And again, we want to pick the elbow, and the elbow is kind of at this point in the curve where it's basically, if you can imagine your elbow going straight up, it's right there. So the value we were interested in is the second one there, and it's 1.009. We're going to just round it to 1. And so what we're going to do going forward is use the value of 1 as our neighborhood distance. So with the first input being 10, which is the number of neighbors, and the second value being 1, the neighborhood distance of 1, our dbScan model will consider a data point to be a part of a cluster if it has 10 other data points within a distance of 1. And we'll see that this model actually works pretty well. So one thing worth noting is that if we didn't pick, the first time I did this, I actually had a typo and didn't pick v4 here. Like I mentioned, I picked v5, and it turns out v5 stinks for this approach, and the value of 1 in that case gave me really, really bad results. And I didn't actually do this plotting. I plotted it for the correct one and then had a typo. So you have to be careful when you pick these values. Just don't be like me and make silly typos. So in this script, we'll do the static, what we did before with the neural network for the iris data set. We'll do the static part of it first. We're going to import our data. We're going to quantize it. In this case, thankfully, it's already quantized. The class column is already... the class column is already just an integer. It's a 0 corresponds to a valid purchase, whereas a 1 corresponds to a fraudulent purchase. So thankfully, there's nothing for us to do there. And what we're going to do is we're going to create our dbScan model. We're going to fit it to our data with, once again, a nearest neighbor distance of 1 and the number of samples in the neighborhood that are required to consider something a core point is 10, and we will fit it to our input data. And so we'll return these labels, and the labels are basically the model's predictions. So again, here we have the same type of thing that we expect. We create an empty NumPy array, and then we iterate through. We gather values from our table into our NumPy array, and we'll return it. And then in here, we'll do the same thing, and we will convert the data from the we will extract predictions from our NumPy array and insert them back into our table, and we will apply our model. So we will call learn. Our input table is called train data, which corresponds to hours 12 through 16 of our data set. We will apply our function, which fits the model and returns the fitted model's classifications. We will give it the columns it expects and convert them into a NumPy array using this function here. We will store our output in a new column called predicted class, and we will get the values from that NumPy array and return them into a table using this dbScan scatter function. And then I just want to do it on the entire data set at once, so I'm going to give it the size of the table itself. And so we run this, and it'll take a bit. dbScan is pretty slow. So it actually is kind of an interesting problem for using dbScan on live data because of the way my dbScan model actually behaves and the answers it gives us. We can actually make a really simple implementation of a live dbScan cluster. Excuse me. So here we have our class and our predicted class. We can see that class is just zeros because we're looking for fraud and there isn't a whole ton of it. But it turns out that this model gets about 73% accuracy when it comes to identifying fraudulent purchases. Once Bender's Matplotlib plugin is live, I'm going to add a section to my blog where I make a nice 3D scatter plot and show in a figure how well this model works with some differently colored scatter points and different opacities, and I think it looks kind of cool. But anyway, so last but not least, we will apply a quote-unquote live dbScan model to some live observations. And so last time what we did was we created fake iris measurements and we applied a trained neural network to them. And so this time we're not actually going to use fake measurements. We're going to use real measurements. We're going to use the 4 hours of credit card purchases that come 24 hours, so at the same time of day on the following day as what we trained our model on. And the idea here is that if we were actually going to use something like dbScan to classify credit card fraud, you could have multiple trained dbScan models corresponding to times of day, and then you could apply the corresponding model depending on the current time of the incoming credit card purchases in order to maximize the accuracy of these models. And I'd like to say that 73% is pretty good, but if if I was trying to actually do live analysis and live prediction, I would aim for a higher value. But for a relatively simple model, I think this works really well. So what we're going to do is we're going to replay our the credit card purchases from the following 24 hours using a data frame. So we will convert that training data or the testing data to a data frame. We will get the values and convert them into a NumPy array, and then we'll replay them based on the timestamp. That's this whole function here. That's all it does is it will grab the n number of observations that happen at timestamp t and write them and then sleep for the corresponding amount of time until the next observation is seen, or rather the next purchase happens. So we'll write the live credit card fraud data. We will then, so this function is my quote unquote dbScan for live models. So dbScan actually isn't built for live models. It's really, really slow. But thankfully, because so we know that this dbScan model returns only one cluster. And so a point is either in a cluster or it's noise. If we didn't have this, say, for instance, if our dbScan model returned purchases that fall into 3 clusters, we wouldn't be able to make a simple extension of it. But in this case, all we have to do is we basically take each incoming data point and we determine using the previous 24, the training data, and basically we place the new data point into our training data. We determine if there are 10 points within the data, within a distance of 1 from our new incoming point, and then based on that, we will call it fraud. And so we'll see very similar accuracy here. And once again, we have a new, actually, I think this is just a copy. I think I kept it in here. But basically, we have our gather and our scatter functions, and then we will apply our quote-unquote live dbScan model that's contained within this function to the table. So I'll run this, and we'll start to see some live incoming credit card purchases, and we'll see my model working. So here, it looks like my model guessed incorrectly. But we'll actually see, I think there's one that's a minute or two in that where it correctly guesses that it correctly identifies a fraudulent purchase. And I am pretty okay with the model giving me false positives, because if I'm a credit card holder, I'd much rather occasionally be notified, hey, did you make this purchase? And I say yes, than it miss it altogether. So as far as how accurate this thing actually is, there are, during this, actually, let me share a different screen and I can give the actual results. And then that'll conclude the presentation. I have a little shell script that will spit out the matplotlib figure as well as the official accuracy of the model. Okay. Hopefully, can everyone see that?
Yeah.
Okay, so in here I have a Python function or Python script called dbScan credit card. And it will use the dbScan model. It basically does the exact same thing that I just talked about. But it'll plot it all to, it doesn't do it in real time, and it'll plot it all to a nice figure and then spit out how accurate the model is. Excuse me. It takes a minute though. Okay, so of a total of about 30,000, I don't know, 200 31,200 observations. I guess I'll have to stop sharing and share again to show the actual figure that I want to include in the blog post. But we have 45 total fraudulent purchases. It guesses 33 of them correct. It misses 12 of them, so that's 12 false negatives. And then it has 71 instances of a false positive. And let me just show the figure, and then I guess we'll open it up to questions if anyone has any. So this is the figure. It's a 3D scatter plot of the what dbScan thinks. So the dark blue blob in the center are the valid purchases that dbScan correctly identified. The red opaque points there that you can see in the foreground, those are the fraudulent purchases that dbScan identified correctly. There are a couple of other, I believe, correct identifications behind that blue blob that kind of get blocked out. There are some purple points, which are the false negatives, and which dbScan got wrong. You can't see them because they're inside of that big blue blob there. And then you can see the teal points around the outside, which dbScan calls fraud when in fact they are valid. And yeah, that's it. So.
All right, thanks. Any questions?
I think you mentioned this, but I just want to ask again. How did you determine the V12, V4, V14 as like the primary things to look at?
So let me go back and show you what it looks like. I can make those histogram plots again, and I'll make them for a column where it won't work well. And we can see how they look different from the other ones. Okay. So let me read. I go. I may run out of memory here at some point. It's I have I think I give myself 12 gigs of memory, but even this data set's pretty big. I'm doing a lot of stuff with it, so I may get a transient failure at some point. But then I'll run the script that creates the histogram plots, and we'll do it for, let's see, this one. Yes. Okay. So we're going to do it for, how about V23. So what we saw earlier was that the histogram, we saw not a ton of overlap between the two histograms. And so what we see here is a lot of overlap. So if I show only the valid purchases, you can see they all fall within this tiny little area here. And then if we look at the fraudulent purchases, they also fall largely within this tiny area here.
Yeah.
Given this large amount of overlap, those fraudulent purchases are not spatial outliers. They actually all kind of fall within one big cluster. And because dbScan, actually, let me show a picture of, there's another picture on the wiki page. So dbScan will cluster points. So basically what we would expect with those two is that, we saw this little distribution. We would expect the fraud and the valid purchases to kind of all fall within this blue blob here. And it would not do a very good job of identifying fraud because everything would fall within this little distribution.
Gotcha. Cool.
Yeah, see, I have this particular script in there, and I'm hoping that, when someone reads the blog, they can just change this one variable and they'll run it and they'll say, hey, wait a second, these look way too similar. I don't think that's going to work. But once again, we see a lot of overlap.